Hello everyone. Uh, Hopefully everyone is here. Please mention in the chat so that I will know who are all here. Is anyone here? Good. Hi Mahesh. Hi Swarna. So hopefully I think we can start with the session. Hopefully everything is visible here. So let us start with field extensions. Okay. So basically field extensions are actually very simple, but their usage is more prominent in many areas. So we will first see the basic properties of a field and what do we mean by a field extension in a more linear algebra way, and then we will move into the concept of field extensions, the categories which it has. Fine. So hopefully everyone know what is a field is. Right? Now, so let us consider f and under addition and some operation called multiplication. So we call this f to be a field if it has two binary operations defined on it, in such a way that we will try to define it in a very simpler manner. So if f comma plus is an abelian group, and with respect to the addition there will be something called an additive identity. So with respect to that identity we refer to that identity as 0. So we remove 0 from this set, and with respect to multiplication, f, every non-zero element in f forms an abelian group. So for a set to be abelian group, it has to satisfy 5 properties. So this has 5 properties in it, and this has 5 properties in it. So there are 10 axioms that need to be satisfied, and then without relating these two, we are not going to have something which is beneficial for us. So what do we do is we define the 11th property to be something which combines addition and multiplication, and which we call it as distributive axiom. That is a dot b plus c is a dot b plus a dot c, and a plus b dot c is equal to a dot c plus b dot c. Okay. Now, so hopefully you are very well clear with the definition of a field. So sorry. So whenever a set satisfies these condition with having plus and dot as binary operation, we call that to be a field. Right? Now, given a field, so some basic examples of fields are real numbers under usual addition and multiplication, complex numbers under complex addition and complex multiplication, and the set of all rational numbers will form a field. And there are many more such examples. There are even finite fields. A field which has finite element is said to be a finite field, and there are fields which are finite. Now, let us move into the topic which we are going to discuss today. Before moving into that, we need one more definition, the definition of a vector space. Now, hopefully everyone knows what a vector space is. If V is a non-empty set, and if under some operation plus V comma plus is an abelian group, and we need to fix up a base field, say some F, let F be any field. Now, so this plus is actually a binary operation on V, that is plus is a function from V cross V to V. Now we define another function called another operation which is not necessarily called as binary operation, which is called as scalar multiplication, which is actually a function from V cross F to V. Okay, maybe I will better term it F cross V to V. That is, you take up an element from the field and you take up an element from the space, from the set which you consider, and with it you associate an element alpha dot V, where this alpha dot V lies in the set V. Now, so if with respect to this operation, if it satisfies few necessary conditions, then we call that set V to be a vector space over F. Now, given a field, now going into digging on examples of vector space, the first example which you come across is actually, we can prove it in general. Every field is a vector space over itself. That is, so to define something, to call something to be a vector space, you need a field which is related to it, which is related in some or the other way to it. Now, fix up a field, consider any field. This will form a vector space over itself. F over F is a vector space. Right? So if you call it to be a vector space, you need to define what is a scalar multiplication here. Addition is obviously defined because this is a field. So you can take up the addition. So we call that the vector addition. So your V is F and your F is the same field. Now you need to define what is the scalar multiplication. So as we saw, scalar multiplication is a function from V cross F to V. Since this V is again F, and already since this is a field, you know there is a multiplication for this space field. So actually this scalar multiplication will be a function from F cross F to F, which is nothing but a function on, a binary operation on F. So already we have a binary operation called addition. We take it to be the vector addition, and we need to define what is scalar multiplication. So we have a multiplication defined on the in the field, but since you consider the space to be the field itself, you take the multiplication defined on the field to be the scalar multiplication. So which is obviously well properly defined, and hence with respect to this, you need to check whether it is a vector space. So when you check whether it forms a vector space, the properties which gives us uh, the field axioms, sorry, the axioms which prove it to be a field will directly help us to prove this is a vector space. Okay. So this is the basic idea with which we are going to work throughout in field extensions. That is, every field is a vector space over itself. So whenever you talk about any structure on any set, any non-empty set, say group or ring or field or vector space or anything, you go on to define what is a sub structure on it. What is the structure on a subset of it? That is, you define what is a subgroup, what is a subring, what is a subfield, what is a subspace, etc. Fine. Now, say consider okay, first we will define what is a field extension, and then we will move into why do we need field extension. Now let f be any field. Okay, now let k be a subfield of f. Let k be a subfield of f. That is, it is a field, it is a subset, and it is a field. Fine. Now, if k is a subfield of f, then please listen carefully. If k is a subfield of f, then f is called an field extension of k. Very simple. That is, f and k. Very simply, how can we state this? It is f and k be two fields. If k is a subset of f, sorry, I will sorry. If f is a subset of k, so maybe my notation may vary. Let f and k be two fields. If f is a subset of k and where f is also a field, we have defined it. So we call k to be a field extension of f. From so this is f, this is k, both are fields. So this k is called a extension field. So extension in the sense you are extending it to be it to a larger field. So whenever you have something to be a subfield, we taught it in the other way around. That is, you say f is a subfield of k. Now hereafter we don't refer to it that way. We call k is an extension of field extension of f. Fine. What is the necessity of having a field extension? Now we will slowly build up as we built up yesterday for groups. Now consider a polynomial in with polynomial in the sense, okay, fine, hopefully you know the definition of a polynomial. It is some kind of combination of elements with some variable x. So we will consider only a polynomial with in one variable where the coefficients are from a ring. To define something to be a polynomial, your coefficients must be at least from a ring, so that the set of all polynomials again forms a ring. So what we do is consider a polynomial x square minus 2. Now, our next, always whenever we have some polynomial, we try to search for where it becomes 0. That is, for what value of x it becomes 0. Fine. So maybe I will consider another, maybe I will take up some other polynomial, say 2x minus 3. 2x minus 3. Right? Now, obviously, if I consider this as a polynomial over integers, definitely it does not have a root in integers. Fine. So, but actually we are not having a field now, because z, that is integers under usual addition and multiplication, does not form a field. So what we do is we consider it as a polynomial over q, set of all rational numbers, which is actually a field. Now in q, this has a 0, that is we call it to be a 0, that is the value of x for which this polynomial becomes 0. We will formally define everything later. Now this polynomial has a root in, has a 0 in q. Now, so does every polynomial with coefficients from q have a 0 in q itself? That is what is our next aim is. So let us consider this polynomial, x square minus 2. Now does this polynomial have a 0 in q itself? So whenever we, so obviously the guess for what x is root 2, square root of 2. But clearly we know square root of 2 is not in q. So what we do is, we are in search of a field. We are in search, with q is a field. Now we are in search of a field where this polynomial will have a 0. So what we do is, we are extending this field to some other field where the root lies, the 0 lies, 0 for this polynomial lies. There may be many such fields, not just one, there may be many such fields. So whenever we have ambiguity, such ambiguity, that is there are many fields, what we look at is, we look at the smallest field, smallest possible field, which contains a 0 for this polynomial. So we are in search of the smallest field which contains the 0 of this polynomial. That must be a field. So we are going to construct a field which has a 0 for this. So one such obvious field which contains, not smallest, but one such field which contains 0 of this polynomial is the set of all real numbers, because root 2 belongs to real numbers. And also you can consider it to be no, I don't think so, but you can consider it to be a rational number, sorry, real complex number under complex addition and complex multiplication. So you can consider this every real number to be a complex number by having the imaginary part to be 0. Fine. So before moving on into that part, now, so our next aim is, does every polynomial have 0? That is, every polynomial with coefficients from q have a 0 in R. So let us check next. So you consider a polynomial from R now. So you can consider it to be over q, but still we will consider it to be over R. R under addition and multiplication will form a field. Now consider this polynomial. Now, does the 0 of this polynomial lie in the set of all real numbers? So we are in search of a field. Clearly this does not have a root in the real numbers. This does not have a 0 in real numbers. So what we do is, now we are in search of a field where this polynomial has a root, has a 0. So maybe I may switch words between root and 0. Both refers to same. That is the value of x for which this becomes 0. So now we are in search of a field where this polynomial becomes 0. So obvious choice is the set of all complex numbers. Now the next target is, does every polynomial with coefficients from complex numbers have 0 in complex numbers itself? That is, consider the set of all complex number under complex addition and complex multiplication. Does this field, when we consider any polynomial with coefficients from C, complex numbers, does it have the 0 in C itself? Every polynomial with coefficients from C have the zeros in C itself. So when we check this, it happens to be true that every polynomial with coefficients from C will have a 0 in C. Fine. So maybe we can stop our extension here. So likewise, we are going to, so our ultimate aim is to extend the field so that given a polynomial, it has a 0. As simple as that. Fine. Now, so we move into the basic properties of field extensions now. So as I said, we are going to go entirely in a linear algebra way. So if you have any clarifications till now, please mention it in the chat so that we can have the clarifications and then move on to field extensions, finite extensions first. So do you have any clarifications? Please mention it in the chat. Okay, thank you, AB. So anyone have any clarifications regarding whatever we did till now? Please mention your questions in chat so that we can clarify and move on. Okay, so shall we proceed on with the next one? Fine. So next we define, so as we defined earlier, if f is a subfield of K, we call K is a field extension of F. Right? Now we are going to define what is degree of a field extension. So it is very simple. So since we defined K to be a subfield, so let F be the subfield and K be the superfield, the bigger field. Now, since we define the scalar multiplication as the multiplication in the field itself, this F will form a subspace over K, subspace over the base field F. Fine. Now, Now consider K to be a vector space over F. That is, F is a subfield, K is a bigger field than F. Now consider K to be a vector space over, K is a vector space over itself. Now even since this is a subfield, this is a subset, and it is a field, you can define the scalar multiplication as defined in the multiplication of the field. Obviously every element is going to lie in the field K. It definitely need not lie in F, but it definitely lies in K. So consider K as a F vector space. Consider K to be a F vector space, that is a vector space with scalars from the field F. Now, since this is a vector space, you can please check whether it forms a vector space. It clearly forms a vector space because it is just the operation defined on the field. Fine. Now, so hereafter I will denote the field extension this way. E F K. Sorry, here now I have given K over F. Right? K is a field extension of F. We define degree to be degree of this field extension to be dimension of K when considered as a F vector space. So since K is a vector space over F, it definitely has a dimension. It may be finite or infinite. It doesn't matter. If it may be finite in some cases, it may be infinite in some cases. So whatever it may be, we define the degree of a field extension to be dimension of the vector space K when K is considered as a vector space over F. So and we denote this by K F. Fine. So whenever the degree is finite, whenever an degree of a field extension is finite, we call this extension to be finite extension. Very simple. If whenever the field extension is of finite degree, that is finite degree in the sense whenever the dimension of K over F is finite, that is whenever when considered as a vector space, it has a finite basis, then this field extension is said to be a finite extension. So you need only finite elements to extend the field. Okay. Now, if suppose the degree is not finite, it is said to be an infinite extension, but we don't usually venture much into the infinite extension. Now, this finite extension has a particular property which is going to be very much helpful for us. Okay, let us see what property it has. So if suppose L, so maybe I will write it something like a ladder. So if L is an extension of K, so K is a subfield of L, L is an extension of K, and K is an extension of F. And say suppose that is L is an extension of K and K is an extension of F, and both these extensions are finite. Assume that they are finite. That is, extension of L over K is finite. Let us call it some M. And extension of K over F is finite. Let us call it some N. So you are having three fields where L is a finite extension of K and K is a finite extension of F. Now the obvious guess is L must be a finite extension over F. L must be a finite extension of F because you need only finite elements to go from K to L, and also you need only finite elements to go from F to K, and hence you need only finite elements to go from F to L. But the crucial part doesn't lie here. The crucial part lies by what is the degree of this extension. That is the extension of L over F. What will be the degree of this extension? Okay. So the obvious guess would be, there might be many guesses, but the obvious guess is the product of M and N. That is, degree of L over F is equal to degree of L over K into degree of K over F. Fine. So we need to prove this, but one thing is obvious. L is an extension. L is a field extension of F is very obvious because K is a subfield of L and F is a subfield of K. So F is a subfield of L. Now, when considered as a vector space, it will definitely have a dimension, and we need to show this bases have M into N elements. That is more than enough to show that degree of L over K is degree of L over F is degree of L over K into degree of K over F. That is actually very obvious. The reason is, so consider L over K to be of degree M and K over F to be of degree N. Now, so since when we are actually viewing it as a vector space, so this will have a basis, say some v1, v2, etc. up to vm. Okay, and this will have a basis, say w1, w2, etc. up to wn. Now, since take an arbitrary element in L. Now, since L is a vector space over K, and since L has basis v1, v2 to vm, H can be written as alpha 1 v1 plus etc. alpha m vm, where alpha i's are from K. Fine. Now, take an arbitrary element y in K. Since this is a vector space over F, and w1, w2, wn is the basis, y can be written as some beta 1 w1 plus etc. beta n wn. Fine. By virtue of just what is a basis, you can write it as a linear combination. Now, clearly, if you look here, each where this beta I belong to F. Now clearly each alpha I belong to K. So, and every K will have a linear combination where the scalars are from F. So when you replace for every alpha I, its corresponding linear combination in K with coefficients from F, what we get is a linear combination of this set V1, V1, W1, V1, W2. So maybe I will erase this and write. So what we get is a linear combination of these elements V1, W1, V1, W2, etc. V1, Wn, comma V2, W1, etc. till Vm, Wn. So in a simpler notation, Vi, Wj, where I varies from 1 to etc. up to m and j varies from 1 to etc. up to n. This set appears to, for now, it appears to form a basis. and this set will have m into n elements. And actually by our construction now we have actually shown that this set spans L over F, L with coefficients from F. So it is a trivial exercise to prove that this set will be linearly independent because these two sets are linearly independent, and hence this set is going to form a basis of L over K, L over F, and hence L over F will have degree m into n. Fine. Now this is all about finite extension. This is some basic introduction about finite extension. Now next we will define what is an algebraic extension, and before moving into defining what is an algebraic extension, we will define what is an algebraic element. So I am not going to go deep into the proof, but we are going to look only on the basic ideas. So shall we move into what is an algebraic element? So if you have any clarification in finite extension and how do we calculate the degree, please clarify it in the chat now. So do you have any clarifications regarding finite extension? Please mention it in the chat. So shall we proceed on to algebraic element now then? Okay, fine. Now, so as I said during the motivation for algebraic extension, our ultimate aim is to find a field where given a polynomial it has a 0. Fine. Now, let F be a field. Fine. Now, let K be any field extension of F. Fine. Any field extension. So, consider an element A in K. That is, F is a smaller field. K is an extension of F, field extension of F. Consider an element A in this field. Now, if suppose there is a polynomial with coefficients from F. If suppose there is a polynomial, say a0 plus a1x plus etc. anx power n, a polynomial where each ai belongs to F. If suppose you can find a polynomial, let us call it p of x. If suppose there is a polynomial x, p of x, such that a0 plus a1x plus a2x square plus etc. anx power n, where the coefficients are from the field F, from the smaller field F, and p of a, that is wherever you have x, replace it with a. Right? So a0 plus a1 a plus etc. an a power n. Fine. Now clearly this p of a belongs to K because the coefficients are from the field F and this a is an element of K. So a square will be an element of K, a cube will be an element of K, and hence a power n will be an element of K. Now this P of A is nothing but a linear combination of elements where the scalars are from F, and hence this will be in k. Fine. Now, if suppose this happens to be 0, maybe I will write it in a better way. Consider a in k. If p of a equal to a naught plus a1 a plus etc. an a power n, if this happens to be 0 of the field k, then we call a to be algebraic over f. Then a is said to be algebraic over f. That is, we call an element to be algebraic if it satisfies a polynomial whose coefficients are from a smaller field. As simple as that. Okay. Now let us see some examples. Let us see some examples where this is examples for algebraic elements, and then hopefully I think for today it will be enough. Right. Now consider the field Q under addition and usual multiplication. Fine. One obvious extension of this field is the set of all real numbers. Consider, let this be your f, and k be the set of all real numbers under addition and usual multiplication. Obviously, k is an extension of f. Obviously, k is an extension of f because q is a subset which is again a field, and r is a field with respect to the same addition and multiplication. Now, please, we will check whether given an element it is algebraic over set of all real numbers or not. Fine. So what do we need to show? Say, consider an element, let us say some, consider a to be equal to 4 by 5. Okay. So to show that a, this belongs to r, so you should consider an element from the bigger field. Right. So if a is equal to 4 by 5, consider this. We need to check for a polynomial with coefficients from q, set of all rational numbers, such that this, for that polynomial, when we substitute a, it happens to be a 0. So this a happens to be a 0 for a polynomial whose coefficients are from q. So an obvious choice for this polynomial is, consider p of x is equal to x minus 4 by 5. Clearly, the coefficient of x is 1, which is in q, and minus 4 by 5 is in q, and hence this polynomial. So for this polynomial, p of 4 by 5 is 4 by 5 minus 4 by 5 is equal to 0. And hence 4 by 5 is algebraic over q. Okay. So you call an element of the bigger field to be algebraic over the smaller field. Now if you take any element from q, we are going to do the same procedure. That is, take any element a in q, rational numbers, consider the polynomial p of x is equal to x minus a. Because the coefficient of x is 1 and this minus a belongs to q, this p of x belongs to this p of x is a polynomial with coefficients from q, and hence p of a will be obviously 0, and hence every rational number is algebraic over q. Every element in q is algebraic over q. It doesn't look interesting. Now consider a number which is not in Q, say for example root 2. So our next aim is to check whether there is a polynomial which has coefficients from Q and satisfies, and this root 2 happens to be a 0 of that polynomial. Now, if we can we it is not possible for us to consider the polynomial to be x minus root 2. The reason is the coefficient of x is 1, which is in Q. Fine. But minus root 2 does not belong to Q, and hence we cannot consider this polynomial. So what we do is we consider the polynomial x square minus 2. So when you substitute for x to be root 2 the whole square minus 2, which is 2 minus 2, which is equal to 0. So we have found a polynomial x square minus 2 whose coefficients are from Q, and it satisfies the polynomial. Fine. Satisfies a polynomial whose coefficients are from Q. So our next aim is every element in real numbers algebraic over Q. Given any real number, is it algebraic over Q? The answer is a big no, but the reason we will see it in another class. There are few numbers which are not algebraic over Q. And one more example for algebraic number is, consider C to be a extension of R. So you need to find, let us consider the element I in C. So you need to consider a polynomial whose coefficients are from real numbers such that this I happens to be a 0 of that polynomial. So consider P of x to be x square plus 1. So P of I would be I square plus 1, which is minus 1 plus 1, which is equal to 0. And hence I is algebraic over R. Right? Okay. I think we will wind up here. We'll stop here. So if you have any clarifications, please mention in the chat. Please mention it in the chat so that we will clarify it and move on to the next topic in the next, whenever possible. So this is just a basic introduction about finite extension, field extension, and the specific cases of it, finite extension, and what do you mean by an element to be algebraic over a given field F. So please clarify your doubts in the chat session so that we can clarify if you have any doubts, please. Please do comment on, please do criticize us, because it is going to be helpful for us. Okay, Syed, there is a question from Syed. What about integers? Okay, so here we are considering only about field extensions, and since the integers is not a field, we are not going to venture too much into extension of integers. Actually, integers does not form a field because say for example 2 does not have multiplicative inverse. So we are not going on into ring extensions. This is just field extensions. Okay, hopefully it clarified your doubt. Now there is a doubt from AB. This doubt is, please, sir, please give an example for degree of extension. Okay, good question. Now, maybe I will give a simple example. It will be helpful. So, C is a field extension of